we have representation from Click to Cloud. I thought our friends TUVN will join, but looks like they're not. So anyway, I think so. Maybe we can start. So I think the agenda item we have is I see only one agenda item actually there, and it's a global key value store service which we are building out for our next the regionless cloud environment. So Pang is going to provide us a high-level overview of what that is. So take it over, Pang.
Okay, thank you, Deepak. Let me share. Okay. So it's called the regionless key V service. This is part of the regionless project. And the goal or the motivation is previously we have this regional service where each region would have their own storage, their control plan, and their data plan. So this triangle represents the like a Kubernetes control plan with the scheduler, controllers, and all that. But the problem is each of this is in a separate region. So this is in one region, this is one region. And by having it that way, the cluster metadata is all separated out into different storage, right? If I have some pod here, then for this control plane, it's not able to see this. Similarly, if I have some VPC subnet object in this etcd, the other cluster cannot see it. And the resource is essentially all separated out into different cluster. In transition into the regionless project is to have the control plan stateless, so that the control plan can scale up, can horizontally scale. If we need another region, we can have another control plan, but we call this SCP, that's the stateless control plan. And since the control plan does not contain any state or any metadata, we need this RKV in between. So the RKV will be acting like a big etcd. It stores all the information from all the regions. And so for example, if one region is writing some pod information into this RKV in one region, the one other stateless CP is able to see it and is able to read and write based on from their region. Similarly, one good benefit is for network. If we want to have a global VPC kind of situation, then the VPC object will also be stored in this RKV, and all the region can share. So they're able to see, okay, we only see one the global or regionless VPC, and inside this VPC, we can create our own subnet and so on. So the goal for this, we call this RKV regionless KV service, is to have this layer of storage for this metadata, and we want this to be scalable. We want this to so these are all the specification of this RKV service. So we want this to be geo-distributed. MVCC is support. It should essentially support the same API that the etcd does. In addition, we want this to have like HA. It should be able to do load balancing, and we have replicas because if we have data spread out in one region, if this region goes down, then we probably will lose all the data. So in our design, we want to have for each data set, for each data part, we want to have several replications for that data.
Hey, quick question. So you mentioned MVCC. So you're going to use MVCC for your versions? Because I know etcd supports multiple versions. Is that the plan?
Yeah.
Okay, but MVCC pretty much cleans up the older versions after some time, the garbage collection and all that. But etcd allows you to do a time travel. So you're not going to do the garbage collection? Is that just kind of
it's already there. Actually, that's a good question. The next slide, we'll talk more about.
Okay.
Yeah. So the data store is it's modeled tightly with etcd, and as I said, the replication will have replication for different data, and the store will select where the replication will be stored. So we have, imagine if we have different regions, this is one region, this is another region, and the RQV store itself will manage like where the replication is put, based on like read-write latency. Also, we support different kind of consistency. This is also similar to etcd, where it could be linearizable, it's very strong consistency, or we could support a sequential consistency. Sequential consistency just means the data you put in, or some of the readers, they might not read the most recent data at the same time, but the sequence they read out is always consistent. Apparently, between these two, there's a performance implication. If we want a stronger consistency, then the performance has to suffer.
So sequential would be similar to snapshot isolation, basically. And then,
yeah. So this consistency is about the replication consistency.
Oh, okay.
Yeah. And performance, we did a lot of performance for latency. If you imagine, if the data now is spread out, if the data happen to be stored on the left region, and if we're trying to read it from the right region, then there may be some latency penalty there. So we did some optimization for that. One thing I want to mention is the actual store is in the memory, and currently we are using Redis, but the backend is open. So if we want to replace this backend actual store with currently we're looking into replacing this with Trigori, and we could use other data store, but this is just one thread in-memory store for us, and the RQV will handle all the partition, sharding, replication, and all that.
So with Chagori, you automatically get MVCC. Well, MVCC and all that. I know Redis doesn't have it.
Yeah, Chagori will use that as the backend store for now.
Okay.
Yeah.
Okay.
So this is the data model. If you're familiar with etcd, this is almost the same, where we have an index between the storage and the user. The user will provide a key value pairs, a set of key value pairs. From the index is essentially translate the key value pair, like for a certain key, into its revision versus what are the changes in a certain revision. And the storage, for example, this is Redis, it will take this as a key, it will take the revision as a key, and it will store the key value pairs as the value. So the benefit of having this index is it can improve read performance. For example, if we were doing range query, this is usually implemented with a B tree or the B+ tree. So that allow very fast range query. And by having this kind of setup, this is essentially the MVCC part. So this allowed us to do list watch and to do the transaction. This transaction is etcd's transaction term. It's more like a batch. It's not the MySQL transaction. Yeah. So for example, if I have a hello world coming in, and from the index, it will be transitioned into, oh, for the key hello, this is a certain revision. And based on the revision, we're able to retrieve or put or get that certain revision from the backend store. And the store will return the corresponding value from the key. And if you were writing, we're going to write that into the backend storage. So this is the data model. The development, we have two phases. One is a POC phase. This is a POC. POC is because it's more of a like research project. We implement this without the actual backend store, without the distributed feature, but we want to see how this part works all together. For example, the sharding, we can try different sharding, we can try different index, and we can try different consistent options. So we do have this POC repository that just to implement the key logic from this project. And we call this a code as a design doc. Essentially, with a design doc, we can design all we want, but we are not sure it's going to work. With the code as a design doc, it's easier for communication between team members, and we know for sure that the key function will work. So this is the final goal for the architecture. The green RKVs are the RKV instance. So this would be our service, and the service will also include like index and all that. And this yellow drum thing, those are the storage. Those represent the storage. And in this picture, each region will have their own RKV service, and each region can have a bunch of storage instances. And on top of it, we are providing a caching layer. So the caching layer is just to speed up the read or to speed up the list watch. This is the final goal. The way we
but this is one. This is not like so. This is like a replicated data. The storage at the bottom, the 3 disks, in each region.
Yeah.
So they are fully replicated and all that kind of stuff. So each
the
region,
replication. So that the underlying layer, they don't do any replication itself. The replication is done by all these RKV instances.
Yeah. But but if you're in one region, you see all the information about the other. Okay.
And so you can say this is the goal for us. The way we develop it is split into a few steps or in a few releases. So in our first release, it's only a small part of it. It's like in one region, we have our RKV instance, it has its index. And we have a bunch of storage instances attached to it. So here we're essentially doing some validation. And currently we're at this 0.2 release. So the difference is you can see now we have 2 regions now because some of the storage could end up in a different region. Imagine this to be US West, this is in the US East, or this is the US is in some other country. The final goal is to come to this. So once we're able to deal with data in a different region, then we're going to have a different RKV instance in different region. So so we are here, and the goal is to eventually we are adding all these RKV instance, and eventually all these RKV instance they will talk to each other for read and write. Currently, it's just one RKV instance. It can write data, for example, in this storage, and it can also read data from here. Yeah, and Smart Cache will be there. I want to emphasize here that the RKV, even though we are showing different RKVs, from the user's perspective, the user does not really care is he's accessing this one or this one. Because conceptually it's just one store. Just to show some more complicated graph, this is how it's stored. For example, the yellow is the index. It stores currently in one region, and if we want to write this red data, when the user tries to write this KV pairs, it's going to write 3 replicas. It will pick one of this from here in this AZ, and another AZ is here. And also the third AZ will be somewhere in a different region. So the 3 red pi would be the 3, would represent the 3 replicas in 3 different locations. And one thing to notice here is the location of these replicas are chosen automatically based on some standard. One of the standard is that we do not have the replica in the same AZ, and we try to have one replica in a remote region. Yeah, this is the 0.2 release note. I won't go into the details here. And we did a few improvement. One is, as I said, the partition. We need to consider the fact that some of the data store is far from us, and we have a latency situation. And we did a lot of improvement just to say, how do we partition, how do we select partition or replication so that we are able to balance between the consistency requirement. For example, do we want to have linearizable, or is sequential okay? And we want to balance that with performance. Apparently, if the data is far, it's going to take a while to read and write. So we have a specific way to select the 3 replicas. The idea is for sequential, we have 2, we call this synchronized access. So for example, the write will write 3 replicas, but the call of the write will wait until the first 2 to finish, and then the write will finish. And we have a third one, which is the async replica. The async replica can take its time, but the async one will be writing to a remote region. So we have this kind of setup. And the 2 sync replica, as I said, will be put into at least different AZ, but they will be pretty close. So the latency for the 2 sync replica will be small, like 40 millisecond. That's usually on one coast, like on the US West, that's between US West 1 and US West 2. This one, you can imagine that's in the US East. Yeah. So for the 930 release, or for the 0.2 release, we did a relatively large experiment. This is the setup. So on the left, you can see this is US West, this is US East. The latency between them is about 100 milliseconds. This is just the AWS network latency. And in US East, we are having a few AZs, so the US East 2 and the US East 1. We put a few storage in different AZs in different regions, and the RTV instance for this test is in the US East 1. So in the same region, the latency is about 10 milliseconds. Between different AZs, US East is about 20 milliseconds. And the 2 blue one are the testing benchmark, like the testing utilities. This is the benchmark. This is doing some profiling. And these are like how many storage instances we're using. This on top of that, you can see what kind of machine we use from AWS. So this is a setup for a large scale test. The large scale test result is here. I won't go into too much details, but one of the key goal is to be able to say we are able to store 100 million key value pairs. And this is 100 million key value pairs, but we do store 3 copies of that because we have 3 replicas. These are some latency based on the fact that we are writing in this test, we're using the sequential consistency just to speed up the test. So the write latency is just the 2 synchronized replica to some close by AZs, and the read is from the same region. So that's why you see this is below 10. This is from like 20 to 40 milliseconds. And this is consistency. This is a part of the interesting thing. The store will support the linearizable and the sequential consistency. The linearizable claim usually will just by design. So based on how we design it, we usually can say, oh, we are achieving linearizable. But in this release, we want to say that we have a way to automatically validate this. We don't want to give this claim. So in this release, we're able to use an open source to verify that we achieved the linearizable. And here is a throughput. Basically, if you just look at this number, it does not give you much information. But for us, if we compare this to number that shows the improvement over different release, that the benchmark or the throughput from like 730 July 30 release is around 220. This is the highest we can go back then. This is the highest we can go in this 930 release. So based from some of the improvement internally and some of the, we fixed a few issues, the throughput is much higher than before. As we said here, we are also using this Jaeger profiling. Profiling is just for us to see what happens inside. If we have 3 replicas, how long does it take to write to different replicas? How long does it take to update the index and all that? So here is just to show some examples. All 3 of this will be part of the calls. This longer bar will be the call to, like, this is 100 milliseconds. So this means it's writing to a remote region. And the faster one, like 1.3 millisecond, that's just writing to the same region. And also here, putting index is after writing the data out, we're going to come back and update the index so the reader can see it. So you can see that the update the index does not take much time. Most of the time is spent in writing data in the same coast, like 40 something milliseconds, and the 110 milliseconds to a remote region. This is put, this is get. By having this, it's very convenient for us to see what's happening inside, and we can do some optimization based on this. And this is just more testing data. This is write latency, and if we increase the thread count, like how many clients are accessing the KV store, we see that it's roughly the same. And so that just say that by having 32 threads, we haven't reached the bottleneck of the system yet. So the performance is kind of irrelevant to how many threads we're trying to use. And similarly with read, the same story. The thread count is to the right, so it's not really affecting the read latency of the store. Apparently, if we keep increasing the amount of threads, then actually from some of our tests, we saw that the latencies start to rise. But then some other issue came up. So in this report, we're just showing this part, and we're doing work to further improve the concurrency when we go to higher thread count. This is the throughput. The same story, they read when we, when we increase the thread count, the throughput performance will increase. And that's both for the read and write. So the blue is read, the orange is write. And so we go from 1 thread, 2 thread, all the way to 32 thread. And the throughput in terms of operation per second will also increase. Here, let's see, we have, yeah, so here is interesting. As we said at the beginning, we have different, we offer different options for consistency. So the blue one is the strong consistency. The orange one is the sequential consistency. And the y-axis is the latency for write, for put. And this is the similar as what we expected. For stronger consistency, the latency will be higher, right? We have to wait for all the calls to finish. For sequential consistency, we don't have to wait all the calls, especially if we have a call that goes to the remote region. We don't have to wait for that one to finish. In that case, the latency for the write will be much lower. So this is a comparison between this. This is the opposite of the latency. This is the throughput for very strong consistency. For again, the consistent here is the replication consistency. So for the strong replication consistency, the throughput would be lower comparing to the sequential consistency. I think this is the last one. The last one, actually, this is the validation for consistency. We are using this tool called the Porcupine. This is open source tool. There are different open source tools. This one is written in Go and it's quite easy to use. This is actually what the tool produce when we call our store. I will not go into the details, but here is just to validate that if we put some value for a certain key, once we start to build, once we are able to see the value we just put in, we will not have any other thread see the older version. So if we have, for example, 10 version, I just put in another one that's 11 version. If any of the readers is able to see the 11th version, then there's no other reader that can see the 10th version. If they want to see it, they can see it. But if they just want to see the latest version, like everyone at this moment will see the version 11. So the tool is pretty nice. It helps us validate that we have achieved the linearizability. And the sequential, we have to do some hack into the tool because the tool is not designed to work with sequential, but we changed the tool just a little bit so that we can see that we can validate that we have achieved both linearizability and the sequential consistency. That's pretty much it. As a summary, I want to go back to this one. So this is still the goal. And we are just extending this RKV from a single region to multiple region deployment. And also with this, we are also doing the smart cache. Smart cache, as I said, is just to do some optimization. If the user is reading from a certain region, and it happened to be the case that the data is in a different region, in that case, the smart cache will be caching the data so that if we have another read, then the performance from this region will be faster now. Apparently, the first time if you try to read something that's not here, it takes time to fetch those data. But once that happen once, the data will be stored here, and any read from the same region will be fast. So that's the goal. And the final goal is on the right. And the overall altogether, the goal is to achieve this kind of RKV storage layer in between so that the other party can achieve horizontally scalability. And we want to also provide different consistency level and with the speed optimized. That's all my talk. Thank you. Any question?
Hey, a couple of questions. So I'm still not clear on the sequential consistency model. Is that the same? Because I know in database terminology, they use snapshot isolation consistency. But what that means is if two transactions are accessing the same tuple and one transaction has a lock on it, the second one will be able to use the old version.
Yeah.
Oh, that's what it is. It's pretty much the same thing then. It's the
pretty much it's not really the same. Snapshot just means based on MVCC. For example, we have 10 versions, and MVCC just allow you to have all these versions there. And sequential just say that the version sequence will be consistent. If you read from one reader or different reader, all this reader will always see version 1, version 2, version 3, and version 4. It's not going to be one reader will see version 2, version 1, version 3. The other one see version 1, 2, 3. That's the sequential. The snapshot just means if we have one thread coming in to trying to read it, you'll be able to see part of this revision, and that's your copy. That's your snapshot for your
snapshot.
And another thread can see a different snapshot, and these two can work on their snapshots. So they are not trying to modify the same database at the same time. Otherwise, they have to wait for each other. With snapshot, you can work on your own version.
And then you do optimistic concurrency.
Just so that we don't have to have that kind of log.
So coming back to the question I asked, you maintain multiple versions of MVCC, so you have a garbage collection and all that, or you just let all the versions sit there?
We do have MVCC. So for every key, for example, here, hello, you could have all different versions based on time. And
so you let the versions sit there basically. So you don't clean them up after some time. So let's say I have 4.
We're not cleaning them up yet.
So basically by doing that now you can do a time travel, because in etcd you can do a time travel because your versions stay forever, isn't it? Pretty much.
Yeah.
In etcd. And typically MVCC, they clean it up. There's a garbage collector that runs periodically and that cleans up the versions which are not valid anymore. But then if you do that, then you cannot do a time travel. So, time travel means you want to go back to and see what was, so that was the kind of so in the relational databases, they don't allow you to do time travel, but etcd does actually. So you guys are following the same model.
That's also what we want. Yes. And with the more storage, because etcd is pretty limited on storage size. We have more sites, but we might also have a situation where we want to do some cleanup. For example, for deletion, we don't really. That's more of a maintenance on the.
Because at some point, what if you have under 100 versions? So you may have to do some cleanup.
Yes. The argument is for like a Kubernetes situation. Usually they care about some of the latest versions.
Yeah.
The version is very rare that people, some of them want to go to the first version. Sometimes it does, but if we have too many versions, usually we care about the.
Yes, I agree. So you will have some garbage collector after a while, but right now you don't. That's why.
Yes.
Yeah. Good. Because garbage collection gets very tricky actually, because the databases don't allow time travel actually. They're all the modern databases which have MVCC. But in your case, because you do want to allow time travel, so you have to maintain, so you don't have to be that smart.
Right.
Okay. So Yingguang, I see Yingguang in the call. So she's gonna use your resource manager is gonna use this as the storage layer instead of etcd.
We want to use as long as it can provide all the requirement we need. So right now, I believe it's not support list watch, right?
Correct. It's not there yet. In the design we do have it. It's just in the first few release that's not on the map. But from at this point it's on the map and we have people working.
So I think Redis, if you're using Redis has that capability. You can extend that, isn't it? So Redis should be able to help you there, isn't it? The list watch thing. Redis has some kind of
I remember Redis does have a list watch.
Not that expensive, but you may have to extend it actually.
Yeah,
I remember in Ignite was there, but we had to extend it to do the list watch stuff.
Yeah. For here, basically the API from the outside, the client will think, we want the client to think they are just talking to etcd.
Yeah.
They don't have to care about where the data comes from, what the consistency, whether that's all internal details for the store. So yeah.
Good. I think this is good. So I think a good thing we're recording actually. So the TUVN guys, they should see this video. I'm gonna make sure they better see this video because it's gonna be because the scheduler, the building this.
Scheduler will be one of the clients.
And obviously Yingguang also is gonna use a resource manager is gonna use it too.
I want to emphasize this. Whenever I say client, in this case, the client would be a controller or scheduler. It's not the external client.
Yes. I understand. Yeah. Because in their case, it would be a scheduler in the TUVN. In the case of Yingguang, it would be a resource manager, basically.
Yes.
Yeah. Good. I think this is very good. And then obviously one problem you're not solving, and we talked about it so many times, and that's the unsolved problem in the industry. You have a cache, but the cache does go through, in the serialization, deserialization, so that affects it. But that's a separate issue that we can tackle later on. Because the cache is going to be externalized memory, so it's not going to be part of the scheduler client.
Right.
So you have to do a serialization, deserialization for that call, basically.
Oh, that part, at a certain time, I'll talk to you more.
Yeah. We don't need to worry about it right now. That's fine.
Yeah, one of the team members is designing that part, and that would be a helpful consideration for that.
Actually, so by the way, so you know that I've scheduled a call with the UCLA professor, so they can help us. They have a lot of knowledge about all the serialization thing, and I've talked to them, and most probably we're gonna do collaboration with them actually, the professor.
That's good. Yeah, that'll be.
So they will help us.
Great.
Okay, good. I think this is good. Looks very good. You guys have any questions? Roshan, Click to Cloud guys. So you can see that. So you wanted to see, what are the new things? You can see that this is really very different than typical Kubernetes does or any cloud provider does actually. So you have this giant etcd which goes across regions.
Mm.
You know. So any comment or feedback you guys have, Roshan, Amit?
Not now, Deepak. Like we'll go through some practical one. Like
Yeah, but this is
we'll try
keep
to
that in
implement
mind,
the
though.
same
This is
method.
one of the innovation which we are doing.
Yeah, got it. It's great actually.
Oh, there's one last thing I want to mention. This is probably not the design details, but for other people, especially for external people to try this, we do have, we spend some effort on the deployment. And apparently, if you look at this picture, there's a lot of moving parts involved that they all have to talk to each other correctly. We do provide a set of deployment scripts. We call this one button deploy. Citing
Also, they can so if the click to cloud guys, they want to play with it, they can do that.
Exactly. Yeah.
So you, Roshan and Amit, you guys should try it out when it's standalone. It doesn't have to be part of Arctos. You should play with it. This will be very useful for you guys.
Yeah. So you essentially run one script, and everything is set up based on your configuration, like how many here, how many here. But yeah, just one script, you have everything up, and it's gonna do the test all by itself, and you can see the result.
Yeah, this would be good thing for you guys to try it out, because you can use that in a lot of your customer requirements too. I know you guys are doing big scale use cases. So just a standalone KV store could be without Arctos and anything in the mix. You can probably leverage this functionality.
Yep.
Okay, thumbs up.
Yep.
Yeah.
Okay. Okay, good. This is great. Thanks, Bunk. I know you're on vacation. You need to go camping. Are you doing camping somewhere?
I just finished camping, but having early meeting helped me get up earlier, so I don't want to spend all the time sleeping.
Yeah, I know.
How do you get internet?
Oh no, I'm not camping now. I just came back from camping.
Okay.
Okay, thanks everybody. Thanks for
All right,
joining.
thank you. Yeah.
This was a good presentation. Yeah, thanks.
Thank you, Deepak.
Deepak, can I talk to you after this?
Yes, shall I contact you on Team?
Yes. Okay.
Okay, I'm there. Okay, thanks. Bye everybody.
Bye.
Thank you, everyone.
Bye.
Bye-bye.
Thank
Bye.
you.